All right, everyone, welcome back to our, I guess this is the second review, but this is in part two of what we had with part one last time, because that was going over an exam. So today is the free-for-all sort of review where you guys can ask me pretty much any question you guys want on any of the material that we've worked on so far. So the way we're going to do this, I kind of like the way we did it last time, where we take 3 questions from the chat, and then we'll take 1 question from the in-person people if there is any questions from here. So without further ado, why don't you guys go ahead and spam the chat. One message per person, though, on what you guys want to see. I have a feeling I know what you guys want. Let's see, we have a lot of extrema. I guarantee we're going to do a Lagrange multiplier at some point. A lot of second derivatives. By second order partial, I'm guessing you guys mean doing the chain rule twice. Let's see. Yeah, it seems like a lot of people want to know about question 17 from the practice exam, where you had to do, you had to find partial z, partial u, and then partial squared z, partial u squared. All right, we had a lot of requests for that one, and we even had requests for it before class even started. So let's go ahead and do that one. So I'm going to do practice exam number 17. So in this problem, what they give us is they tell us that z is a function of x and y and has continuous second partial derivatives. Okay. They also tell us that x is going to be v squared minus 2u squared. Oh, can I do that, but change it to where partially y is actually something? Oh, that's actually a good idea. Yeah, because this kind of degenerates because originally y was just equal to 2 times v. But let's stick a u in there for fun and see what happens with that. This problem will be longer, though. I will tell you that, but it'll be a good challenge here. All right, so now we're going to change y into 2uv. So what we want to do is we want to compute 2 things. We want to compute partial z, partial u, and then later on we want to compute partial squared z, partial u squared. All right, so let's draw a tree diagram to see what our chain rule is going to look like. So we have z up on top, and z depends on x and y. And in turn, according to these formulas right here, x and y both depend on u and v. So we end up with like a little bottomless house looking thing right here. So if we want to do our u derivative, we follow all of the possible paths down to u. So we do partial z, partial x, and then partial x, partial u. And then we do partial z, partial y, and partial y, partial. Another way of thinking about this, if you don't like the tree diagram or you're confused by them, another way of thinking about this is if you kind of think of these as fractions and we sort of imagine that we cancel these out, you need to have all of the different ways of getting partial z, partial u. So there's the way where you can cancel out the x's, and there's the way where you can cancel out the y's. That's another way of thinking about the chain rule here. All right, now they didn't give us anything with f here, right? They didn't tell us what type of function it is. So we're kind of just stuck with partial z, partial x, and partial z, partial y. Those are just going to be just there. What we can figure out is partial x, partial u, and partial y, partial u. Okay, so let's see what we get here. We're going to have partial x, partial u, which is going to be negative 4u. And then we have the dz, dx can't do anything with. And then partial y, partial u, according to how I changed the problem, we're going to get 2v. All right, so there we go. So there is our first partial derivative for partial z, partial u. All right, now let's do the second one. And this is where things get a little weird. What I'm doing, remember what a second derivative is. A second derivative is a derivative of a derivative, right? So if I want to find the second derivative, I just do the u derivative of what I just found. So what I'm doing is I'm doing the u derivative of negative 4u dz dx plus 2v dz dy. All right, so let's see here. Let's try to do this derivative. So for the first part, let's do the u derivative of this term. So we have negative 4u times dz dx, right? So that means since we have two things multiplied together, we're going to do a product rule here. So I'm going to do the derivative of the first part, which will be negative 4, and then I'll leave dz dx alone. Then what I'm going to do is I'll leave the negative 4u alone, and I'm going to do the u derivative of partial z partial x. And I'll come back to what that means in a minute. Next, I'm going to come over here and do the u derivative of this. But since we just have a 2v and that's a constant with respect to u, we can just move that out. And I'm really doing the u derivative of partial z partial y. Okay, now let's think carefully about, say, what this means right here. The u derivative of partial z partial x. What I want to know is this. Partial z partial x is my function now, and I want to know its u derivative. This by the way, is separate from what I'm doing here. I'm trying to figure this out on the side, and then I'll plug it back in. So I want to know the u derivative of this function. Well, how did I figure out a u derivative earlier? I used the chain rule. So I had partial z partial u is all of this stuff. So this is going to be the same thing, only instead of every time we write a z, we're going to write a partial z partial x instead. So this is going to be partial z partial x, and then we have partial x partial u, and then we have partial z partial x partial y, and partial y partial u. So effectively what I did was I just reused the chain rule up here, only I just replaced the z with partial z partial x. That's all I did differently here. All right, so then what is this going to give us? Well, the x derivative of an x derivative is the second x derivative. So this is how the second derivatives start appearing, is we're doing an x derivative of an x derivative here. And then partial x partial u, we actually already figured out what that was earlier. That's going to be negative 4u. Okay, now we're going to have partial squared z partial y partial x. So this is actually a mixed partial here. And then we have partial y partial u, which we also concluded earlier was 2v. Okay, so that's going to let us put this back in here. So we're going to have negative 4 partial z partial x minus 4u times negative 4u partial squared z partial x squared plus 2v partial squared z partial y partial x. Now remember, we still need to do this other part over here. I made the problem worse, so we have to do this part. So this is where we're going to get our other partials. Why are you allowed to change y? I mean, I just made it a different problem. That's all I did here. I just made this into a different problem. So now it's, I'm going to call this practice exam 17 prime here. I just changed this. All right. So now we need to do the u derivative of partial z partial y. Okay, well then that's going to be exactly the same how we just did this one right here. So we're going to do partial and then partial z partial y partial u. Okay, well, if we use the same reasoning that we did up here, we're going to have a derivative inside here. And then we're going to have the derivative inside here as well. Okay, so let's see what we get out of this. So this is the x derivative of a y derivative. So this is partial squared z, And then we have partial y, partial x. I'm going to write it in the same order that this one is, because remember, the mixed partials, it doesn't matter what order we do them in, as long as they're continuous. And they said that these were continuous in the beginning. So I'm just going to write them in the same order. All right. So we have that. And then we have partial x, partial u again, which for the third time is negative 4u. And then we have the second y derivative of z. And then we have partial y, partial u, which is also for the third time 2v. So then we're going to take all of this and we're going to put it into here because we wanted the u derivative of partial z, partial y. Why didn't I do plus 2 dz dy in the second derivative? So I'm not sure where you're talking about with that. Let's see. Yeah, I'm sorry. I'm not exactly sure where you're talking about. Talking about above this line, so right here. So all we're doing is we're just recreating the chain rule that we started with. So rather than z's for all of these, we're instead putting partial z, partial y for all of these. Oh, the big horizontal line splitting the page. Oh, I put that there because this was an aside. So I'm going to put another line there. So this stuff was all me computing this. And then now I'm on another aside. So this also could be split up. So this is another aside where I'm doing this right here. All right. So now let's put everything together because we're pretty much done now. So our second u derivative is going to be negative 4 dz dx minus, well, let's see, let's distribute this negative 4u through here. So we have plus 16u squared dz squared dx squared minus 8uv d squared z dy dx. All right, now with this part, I'm going to do 2v times this. So that's actually going to give us another minus 8uv, and then the mixed partial. Oops, forgot partial symbol. All right, so that's going to be 2v times this right here. And then I have 2v times this, so I have plus 4v squared, partial squared z, partial y squared. There we go. There's our gargantuan second derivative using the chain rule with two different variables. So that's a pretty nasty chain rule right there. But hey, you guys told me to make it harder, so I did my job here. But the key thing that I want to get through here is these two steps here. If you want to do the u derivative of something that's already been differentiated, you need to do a whole chain rule for that. So the chain rule for second derivatives is kind of nasty because you have to do that. Did I perform the product rule twice? I think I may have even done it more than twice. I did it, I did the u derivative here, and actually I only did it once. Now I'm looking at it. I did the product rule here because I had negative 4u times partial z partial x. And I didn't need to do the product rule here because the u derivative of 2v will be 0. So I just kind of did this as a constant. The one on the practice exam is easier. Yeah, because we didn't have a dependence on, we didn't have it. I stuck this extra u in here to make it harder. So yeah, it definitely is easier because most of these things end up being 0. All right. So let's see here. So we got that one. That was good practice with our second derivatives and using the chain rule here. All right, so let's get another question. So it's time to spam your answer or spam your questions. And remember, only one message per person. Can't have the same person saying a bunch of things in a row. Okay, it definitely seems like some kind of extremo. Let's see here. It seems like in particular, you guys want to do an extreme problem with distance. I'm getting that vibe from this chat. Let's see. Is there one like that on the practice exam?
Yeah.
Yeah, which one was that on the practice exam?
It was from the surface to the origin, maybe 10 or 11.
Oh, here. Oh, yeah, here. It's number 10. Find the maximum distance from the origin to the curve, etc. Okay. Yeah, I'm going to do number 10 from the practice exam because that covers, that uses, it's going to deal with extrema, and then we have a distance. All right. So practice exam 10. I'm not going to make this one harder. I'm just going to keep this one, keep this one the same level. Oops, up a little too high. All right, we have 3x squared plus 2xy plus 3y squared is 1. All right, and we want to find the maximum distance from the origin to this curve. Okay, so the thing we're trying to find an extrema of is the distance function. Now, normally the distance function to the origin would be square root of x squared plus y squared, right? But the thing is that if you want to maximize something under a square, or you want to maximize the square root of something, that's just the same thing as maximizing whatever is under your square root, right? So rather than this, I'm going to capitalize what I guess I'll call big D, which is little d squared, which will be x squared plus y squared. This is really what I want to maximize. But at the end, when I get a value for this, I can't forget to take the square root of it. So it's easy to pick the answer 1/2 for this. I think I did this one earlier. I think it's easy to make the mistake and pick 1/2 for this when it should be 1/√2, as we'll see. All right, so this is what we want to maximize. And then the constraint is this. And a question I get fairly often is, how do I tell the difference between the constraint equation and sometimes what's called the objective function, what we're trying to maximize? And the answer is the constraint function has all of your equation equal to some number. So in this case, we had 3x squared plus 2xy plus 3y squared equals a particular number. Whereas this, the distance, we're not setting this equal to a particular number. We're trying to find out what number it could be. Oh yeah, another way of thinking about it is the constraint has an equal sign. Well, I guess this technically does too, but it has an equal sign and there's stuff over there, not just the name of the function. That's another way of thinking about it. All right. So let's see here. For this, I'm going to use Lagrange multipliers, because let's practice using that. So I'm going to call this guy my f of xy, and then the constraint will be g of xy here. All right, so Lagrange multipliers here dictate that the gradient of f is lambda times the gradient of g. All right, so what's the gradient of f? Well, we have 2x and 2y for that. And then we have lambda, and then we have the gradient of g, which let's see, it's going to be 6x plus 2y. And then the y derivative of this will be 2x plus 6y here. All right. When do we use Lagrange? It's usually a good idea. Oh yeah, Charlotta has the right answer. Yeah, it's usually a good idea to use it when you just have one equation for your constraint. You don't have something like a box with 4 different sides here. But sometimes if your constraint looks a lot like something inside your function that you're trying to maximize or minimize, then substitution may be better in that particular case. But I usually default to Lagrange multipliers. All right, so let's see here. So let's write out our equation. So we have 2x is 6 lambda x plus 2 lambda y. And then we have 2y is going to be 2 lambda x plus 6 lambda y. And then finally, we have 3x squared plus 2xy plus 3y squared is 1. So these are our 3 equations here. All right. Now what we need to do is we need to solve this system of equations. And Tristan has the right idea here. We're going to multiply by x and y separately. So we're going to multiply this equation by y. So we're going to multiply by y. And we're going to get 2xy is 6 lambda xy plus 2 lambda y squared. Then we're going to multiply this equation by x. So we're going to have 2xy is 2 lambda x squared plus 6. 6 lambda xy. Okay. So we get these 2 equations here. And then one thing we can do with them is since they're both equal to 2xy, we can set them equal to each other. Okay. So we have 6 lambda xy plus 2 lambda y squared is 2 lambda x squared plus 6 lambda xy right here. Now, the nice thing about this is that we could just subtract and cancel those guys out right here. So then we end up with the equation 2 lambda y squared equals 2 lambda x squared here. Now, there's 2 possibilities for this. The first possibility is lambda equals 0. But that really wouldn't be too great, because if we do lambda equals 0 and we bring that back up here, that means that 2x and 2y need to be 0. So that means that our point will be the origin, but the origin is not on this constraint curve. So that's a dead end. We're not going to go that way. Can lambda ever equal 0? Yeah, sometimes we do use lambda equals 0. But when you do that, you need to make sure that it makes sense with your problem. You need to make sure it satisfies your constraint. Yeah, the problem, what's happening is the problem is trying to let you know that, oh, hey, the closest thing you can get to the origin is being at the origin. But unfortunately, that doesn't play nice with our constraint curve here. That's what lambda equals 0 is trying to tell us, but it doesn't work for this problem. All right, well, if lambda is not 0, then that allows us to divide by lambda and 2, because 2 is not 0 either. And we have y squared is equal to x squared. And if we take a square root, we have y will be plus or minus x. All right. So then now what we can do here is we can take this and put it into our constraint equation. So every time I see a y, I'm going to replace it. I'll do y as x first, and then I'll do y as negative x. Okay, so let's see here. If I plug in y equals x here, I have 3x squared plus 2x squared plus 3x squared is 1. All right, so that combined is going to give me 8x squared is 1. So x squared will be 1/8. And so x can be plus or minus 1 over root 8. All right, and then now we're going to do y as negative x. So we're still going to have 3x squared, but this time we're going to have minus 2x squared, and then we have plus 3x squared. All right, so 3 minus 2 plus 3 is 4. And then so we have x squared is 1/4. So x is going to be plus or minus 1/2 here. All right. So let's see here. So we have x is going to be plus or minus 1 over root 8, meaning that y will also be plus or minus 1 over root 8 here. All right. So then when we take that and put it into our distance formula, we end up with 1/8 plus 1/8. That's going to give us 1/4. And then we take the square root of that, and we get 1/2 here. All right. Wait, what are the arrows with x, y, and x? Is D the distance formula? Oh, no, sorry. D is the distance formula squared. So this is little d right here. But it doesn't matter. We're trying to figure out the distance here. Now, we could do the same thing with these 1/2s. So let's check this out. So if x is plus or minus 1/2, then y is minus plus 1/2. It has to have the opposite sign here. How do we get d is the square root of x squared plus y squared at the beginning? That's the distance formula from the origin. So that's how far a given xy value is from the origin. All right. And then we do this, and our distance is the square root of 1/2 squared, so 1/4 plus 1/4. So we have the square root of 1/2, or 1/√2. Now we wanted the maximum distance from the origin to the curve, and this will be a bigger number. So we're going to get 1/√2 here. Why is it 1/8 squared? Oh yeah, you just got the answer. It's 1/√8, and then we square it. All right, so there we go. So that's how we get 1/√2 for this. This is an excellent example of Lagrange multipliers. So we have to solve a nonlinear system, which often has these branching paths, not all of which will make sense. Then we get our solutions to this, and we have to plug those into the constraint to get our possible points. And then we just do a little contest to see which point is going to give us our answer. So we wanted to find the biggest answer, and 1/√2 is bigger than 1/2 right here. Wasn't d squared f of xy? Yeah, but remember, the points that we got for doing this with d squared will also be the extrema for just regular d. Because if you want to maximize something under a square root, then that's just the same thing as maximizing what is under the square root. So if you want to maximize the square root, just maximize the stuff underneath it. If you did a Lagrange with a straight that's an inequality, would you test the bounds? With that one, with the inequality, that's kind of a different type of problem. You would first do the critical points, and then you would use Lagrange, although you wouldn't have to test the bounds specifically for those. You usually just test the bounds when you're doing the substitution method. So we didn't have to take the square root at the end to get the max. We sure did, because we have a fourth plus a fourth is root 1/2 is 1/√2 right here. So we did end up using the square root here. All right, so there's that one. So we did a Lagrange multiplier problem. When you use Lagrange, should you test critical points? If it's an inequality type region, yes, you should test the critical points in the interior. All right, so that's time for our third question. Then we'll give the live audience a chance to ask a question. So let's see here. Let's see what you guys want. Okay, there's some demand for this quiz 4 question 1. Let's see, some for tangent planes, some for differentials. It's pretty even split here, I think. All right, it's like a big battle between tangent planes and then quiz 4 number 1. All right, let's do quiz 4 number 1, and then we'll probably end up doing the tangent plane ones after, or after the audience has a question. Although they might have that as a question. Let me pull up quiz 4 real quick. And I guess people have different versions of it, so I'm just going to pick a version and do it. Okay. So let's see here. So the version I got randomly, quiz 4 number 1, find a direction such that the f of xy being the square root of x minus 2y decreases most rapidly at the point 2, -1. All right. So let's see here. So we want to find the direction of greatest decrease. So can anyone tell me in words what I'm looking for? That's right. We're looking for the negative of the gradient. That's right. So the direction which will decrease the most rapidly will be the negative of the gradient. So that's what we're going to look for here. Okay. So let's just find our gradient and then we'll negate it. All right. So the x derivative of this is going to be 1 over 2 root x minus 2y. And then the y derivative of this will be negative 1 over the square root of x minus 2y. And I got a negative here and I canceled out the 2 because I would multiply by -2 for my chain rule here. Okay, there's my gradient. So that means the negative of my gradient will be 1 or -1 over 2 root this stuff, and then +1 over root x minus 2y. All right, now my negative gradient at the point 2, -1, let's see what that's going to be. Well, let's see, we're going to have -1 over 2. X is 2, y is -1. So everything underneath the square root will be a 4. So this is going to end up being -1/4. And then this is going to be 1/2. Okay, so there we go. So that's our direction of greatest decrease, though it doesn't appear that this is an answer choice. So if we don't see this as an answer choice, we need to find something that has the same proportion that this vector does. So the y value is -2 times the x value. So let's see if we have an option like that. 1, 2, no, that's not an option there. Oh, -2, 4. Yeah, that'll do it. That's -2 times 2 here. Why is y not negative and x is negative? Because we're doing the negative of the gradient here. We want to find the direction of fastest decrease for this one.
Professor, when you say proportional, you mean positively proportional, right? Like it can't be that both of them are
Right.
proportionally.
Yeah, thank you for clarifying. Yeah, so this needs to be negative, and then this needs to be positive. That's right. So the only answer choice that has that as the proportion and keeps the same sign will be -2, 4. If we flip the sign the other way, then that would be in the direction of the gradient, which is the opposite of what we want. So we have to multiply it by the same number. Yes, so -1/4 times -2 is 1/2. -2 times -2 is 4. That's what I'm talking about here. All right. So y is perpendicular to the gradient the least amount of change. Imagine that you're on a really steep hill, right? And the direction of the gradient is pointing up the hill. The negative gradient is pointing down the hill. And then perpendicular to the gradient is just kind of moving side to side on the hill. So if you're moving side to side on the hill, you're not changing your height. That's why being perpendicular to the gradient has no change. All right. Can you just divide the, oh, I missed that. If this question asks for no change, what will we have done differently? You need to find, so let's say we were looking for the direction of no change, because I think some of the people that requested this wanted that. So let's see, our gradient, our regular gradient, will be 1/4 -1/2. So what we need to do in order to get no change is we need to dot this with whatever direction that we have, and we need that to be 0. Because like we were just talking about, if you go perpendicular to the gradient, you're not going to change at all. So you would just dot each of these vectors with the gradient and then see which one would end up giving you 0 right here. That would be the difference if they ask for no change. And remember, yes, so that's another thing you can do. Remember that you could always make a vector that's perpendicular by flipping the order of these and then changing the sign of one of them. So the vector that we're looking for should be something like this, or maybe both of the signs are negative here. So yeah, thanks for reminding us about that, Tristan. All right, so I think we got that problem here. To reiterate, we find the gradient, negate it if it's decreasing, and then dot product each possible answer. If you're, well, it depends on what type of problem you're doing. So if you want to have it be no change at all, then you would just dot the regular gradient with all this. Or you could do the negative gradient. It doesn't really matter. But you would just dot the gradient with all of them and see which one will give you 0. All righty. So now it's time for the in-person people to ask something if they want. Does anyone have a question here you guys want to ask? Or did anything in the chat seem appealing? All right, let's take a look at that. So we got a request to do last question on this quiz. And I'm assuming you don't mean ripping up the scratch paper.
Yeah, that was so confusing.
All right, let's see. Okay, so this one's a Lagrange multiplier. All right. All right, so this is quiz 4, number 6. So we get more practice with Lagrange multipliers here. All right, so find the max and min values of f of xy is x minus 2y plus 1. And then our constraint is that we need g of xy 2x squared plus y squared. That needs to equal 2 right here. Wait, we already, oh, did Dr. Huang do this question, or are you talking about something else in the chat? Oh, fall 19 question. Oh yeah, anything from fall of 19. Yeah, that you can look up Dr. Huang's review, and I think she's done all of those. All right, so let's see here. So let's do Lagrange multipliers here. So we have the gradient of f should be lambda times the gradient of g. All right, the gradient of f, thankfully that's not too hard. We're going to have 1, negative 2 for that. And then for lambda here, we're going to have 4x and then 2y. And then remember, we also have our constraint equation as well. So if we write out the 3 equations that we have 1 is 4 lambda x, negative 2 is 2 lambda y, and then we have our constraint. 2x squared plus y squared is 2. All right. So what I'm going to do here is I'm going to solve for x and y with these. So 1 over 4 lambda is my x. And then we have negative 1 over lambda is y right here. Now, what am I going to do with this information? I'm going to plug it into my constraint here because I use this equation, I want to use this one. And that's one little guide that can kind of help you through this. You're inevitably going to use all of your equations when you do Lagrange multipliers, or at least you should. You should end up using all of your equations. So make sure that if you're on the right track, you're using all of them. All right, so I plug this in for x. So I have 1 over 4 lambda squared. Let's see, y squared, that'll just be 1 over lambda squared. And we have 2. All right, so this seems like we have 1 over 8 lambda squared plus 1 over lambda squared. is 2. I'm going to multiply by 8 lambda squared. So I have 1 plus 8 is 16 lambda squared. So 9 is 16 lambda squared. So 9/16 is lambda squared. And lambda is going to be plus or minus 3/4. All right. So that's going to be, those are going to be our lambda values. Now, since we know what lambda is, that means we can go back and put those in and get some x and y values. So let's make our little chart with our x and y values and what values they have on the function. So x, let's do the positive version first. So with lambda positive, we have, let's see, 3/4 times the 4 here will give me 1/3 for x. And then for y, it's the negative reciprocal of it, so it's -4/3. All right, and then the other point will be where we use negative lambda, that will just flip the signs on these. Lambda neg. All right, and then we just need to plug these into the function all the way back up here and see which one is going to be biggest and which one's going to be smallest right here. All right, so let's see. X is 1/3 minus 2 times -4/3, so that's plus 8/3. So we have 9/3, which is 3, plus 1 gives us 4. All right, and then if we do this the other way, we have -1/3 minus 2 times 4/3, so that's going to be -3 combined. And then we add 1, and we get -2. So this is going to be our max, and this is going to be our minimum right here. All right, so there we go. So there's that problem.
On the question, it said, how many solutions does it have? I don't know the answer to that question.
Let's see. So on the question itself, it says find lambda, and then it says lambda is plus or minus. So we would type in 3/4, and then find the maximum and minimum values. Then it just wants the values. I mean, maybe you got a different version of the question.
Yeah, sorry, Professor, but like my question was, what if the lambdas are different? Like the value of lambda is different.
Oh, well, then we would just plug in that value of lambda, and that would give us another point to check.
Oh, no, but like for the question which I got, everything was getting cancelled out on either side, and like it was getting like the x thing was getting cancelled out and the y thing was getting cancelled out, and we were getting two different values for lambda. That was like one of the questions in question 6. Like it was in some other set.
If you end up getting something like lambda equals lambda or some kind of absurd thing from your equations, that means you reuse the same equation too much.
I was getting something like lambda equals half and lambda equals 1/4 or something like that. Like two different values of lambda.
Oh, well then, yeah, so you would just split up the problem at that point and do one part for lambda as a half, and then you do one part for lambda as a quarter.
Oh, that makes sense. Thank you.
Yeah, if you ever get like multiple things that would be the solution, you just have to kind of go down the path for each of them. Now be wary though, because sometimes they don't really make sense with the problem, especially if you get 0 for something. I'd watch out for zeros. But yeah. I always get confused what to plug in where. Unfortunately, in nonlinear equations, it's kind of hard to give like a general guide to solving nonlinear equations. In fact, I don't think one exists. But we already figured out there are kind of two varieties of these problems I see most often. There's ones where we should probably solve for x and y in terms of lambda and then plug that into the constraint. That happens when the equations look kind of like this and they're relatively simple. The other type of problem I see pretty often is where we try to set the two non-constraint equations equal to each other. That seems also like a pretty common way to do the problem as well. How do we do a problem with two constraints again? Well, remember with that, if we have h of xy is some number, then we're going to add mu, and then we have the gradient of h. That would be how we would handle multiple constraints. All right. When we use the original equation's derivative, that would be more like the substitution method. But anyways, now it's time for, oh, Dr. Huang said that won't be on there? Okay, all right, well then I guess it won't, you don't need to worry about that then. All right. So let's see here. Yeah, let's look at the chat for a question. Let's see how much time we have left here. Ooh, only 4 minutes. I think the tangent plane one would be more likely to fit into 4 minutes, so I'm going to do that. Let's see, where's a good tangent plane one? I know there's one on this practice exam.
Is there a way for like the tangent plane you could just like, I guess, go over like the different types of equations to use in the different cases?
Yeah, we could talk about that. Here, I want to take a look at question 8 though. So let's see here. So remember that there are 2 different equations for your tangent plane. So in this problem, let's see, we have f of xy is x squared plus y squared plus xy minus x plus 4y. And we want to find where the tangent plane is horizontal. All right. So we want to know where this is going to happen. So what do you guys think? How are we going to do this? How do we find out where a tangent plane is going to be horizontal? Yeah, that's right. So you're looking for when the gradient is going to be 0. Because here are the 2 equations for the tangent plane. I'll kind of explain this as I do this problem. So the first one is z is f of ab plus partial f partial x at ab times x minus a. And then we have partial f partial y at ab times y minus b. I would do this one, so use this if z is on its own. So if I wanted to find a tangent plane for this, all of this stuff is equal to f of x, y, or z, I would probably use this formula. But the other formula for the tangent plane is if we have f of x, y, z equaling some number. So all of the variables are on one side right here. So that one would be partial f partial, or let's do x. X minus a, partial f partial y, y minus b, and then partial f partial z, z minus c, or f of ab, is equal to 0. So for this one, use this if z is mixed in to the equation. So if it looks like a situation where you might have to do implicit differentiation or something, then you want to use this equation more likely. But anyways, back to this problem though, they want to find out whether the tangent plane is horizontal, meaning that z is just going to equal some particular value. So that means that we want these 2 guys to be 0, so we don't have them in there, and then z is just equal to the value. So we're going to look at the gradient of f and see where that's 0. All right, so we have 2x plus y minus 1. All right. And then the y derivative is 2y plus x plus 4. All right, and we want these guys to be 0. All right, so if I set this guy equal to 0, I have y is 1 minus 2x. Because if I add the 1, subtract the 2x, I have y as that. I'm going to take that and put it into here. So I have 2 times 1 minus 2x plus x plus 4 is 0. So I have 2 minus 4x. Oh, is that a plus ab at the end of the second equation? Oh, this is f of ab. It's just another name for c here. Anyways, we have plus x plus 4 is 0. Let's see. We're going to get 6 here. We have negative 3x plus 6 is 0. That means x has got to be 2. So x is going to be 2. And then y, if I plug this back in here, y is going to end up being negative 3. So we're going to have a horizontal tangent plane at the point 2, negative 3. And some people said critical points as well. That's also a good way of thinking about it, because remember, a critical point is where we're going to have some kind of a flat tangent plane. So that might be at a max if it's at the top of the hill. It might be at the bottom if it's a minimum, or maybe a saddle point as well. All right, so just set the gradient equal to 0. Yeah, if you want a horizontal tangent plane, yeah, just set the gradient equal to 0. If you want a tangent plane that's not horizontal, like let's say we want our tangent plane, I'll say this real quick. Let's say we want our tangent plane parallel to, I don't know, like x plus 2y plus 3z is like 6. Then we need to set our gradient equal to a multiple of 1, 2, 3, which is the normal vector of this. So that's how we do it if we want it to be parallel to something that is not just 0, or is not going to be horizontal. All right, unfortunately, that's all the time I have for now, but I'm going to be checking my email pretty often this afternoon, like especially between like 4 and 5 p.m. So if you guys have any remaining questions, I'll do my best to respond to those over email. And yeah, best of luck tonight. I hope you guys do well, and I will see you on Monday.